Welcome back. Man, after the last one, I was talking for almost an hour. This one's shorter. Oh, I gotta play this. I gotta go ahead and play this. New slideshow. So, yeah, this one will be shorter. Don't worry. We're at chapter 2, and here are the linear objectives. I'm not gonna read them. You can read them on your own. That would just take unnecessary time for you to go through here. Atoms. Atoms is a Greek idea, and they thought that atoms were made of four elements: earth, wind, fire, water, and they um, they are kind of like little tiny spheres. And there were some problems with this. They later turned fire into something called phlogiston, and then we also said that it gave metal their luster, their shininess. So that's a problem we'll talk about later. It's kind of interesting, but it's a Greek idea. And also, we can get to the point that matter cannot be subdivided past an atom. That's not true. Atoms, you can break them down to protons, neutrons, and electrons. So, anyways, let's start with the conservation of mass. This is Lavoisier. So, and the French folks. A husband and wife pair, they like to do science together. Literally, that's you can see them. They like to do scientific experiments together. And they did enough experiments and they found out the law of conservation of mass, that during a chemical or physical process, matter is neither created nor destroyed. That is the law of conservation of mass. And for instance, here you can take mercuric oxide, also known as cinnabar, to form mercury and oxygen in a set ratio. And you're not losing mass, you're not gaining mass. The Greeks had a hard time with this because they're like, well, mercury becomes, they burn it and it turns orangish or reddish color and it gets heavier. Like, what the heck's going on? So they thought that fire and wind were kind of like, or fire and air were kind of like anti gravity, and earth and water were sort of like gravity. But there were still some things. So if you burned metals, they got heavier, but if you burned wood, it got lighter. So they were like, well, we don't know what's going on, so we're going to blame it on the gods or something like that. So, of course, we have a better explanation nowadays with atoms. But let's go on and talk about, we're building up to atomic theory, law of definite proportions. A compound always has the same elements in specific definite proportions. So copper carbonate always has the same composition. So for instance here, 10 grams of lead, 1.55 grams of sulfur will always form lead sulfide. So if you have an excess of one thing, you will get the same amount of the compound, but then excess of the reactants. So you cannot change the compound there and the ratio of that. And moving on, we can have the law of multiple proportions and law of multiple proportions. So you can have the same two elements, but you can get different compounds and different ratios. For instance, so I already mentioned with water. Water can be H2O and it can be H2O2. So it can be water and hydrogen peroxide. Two different compounds, two very different things. And this is also illustrated here with nitrogen oxides of nitrogen. So here comes Dalton, and look at that guy. How could you not believe Dalton? He came up with the idea of atomic theory. Well, it wasn't his originally, as the Greeks, but much more well formed than the Greeks. And he said these things here, that they have atoms made, or matters made of atoms. Each atom of them are the same, but they differ from other elements. So this one here, that's an incorrect statement. I'll talk about that later because of isotopes. And compounds are formed when atoms of different elements combine in fixed proportions. So that's the law of both multiple proportions and definite proportions. So compound definite proportions have set ratios, and you can form different compounds from different ratios. And a chemical reaction involves a rearrangement of these atoms. So, and this may seem all fine and dandy to us right now, but the thing is that can you imagine trying to sell this? Like, imagine you're a salesperson, like, all right, I got these things you can't see. I'm gonna call them atoms, and you can't see them, but when they react, they just rearrange. And you're like, what's your proof? I'm like, well, we have this, So I mean, there is proof for it. The proof for this, I'm gonna go backwards. here is the proof that you have the definite proportions and the multiple proportions. That's the proof of this, is combining those two experiments, and also the law of conservation of mass. So, but nowadays we're like, show me, I want to see it. But I'll show you some pictures soon. But right here, much of it has been modified. Isotopes. Isotopes are elements. We'll talk about this later, but an element is defined by some number of protons. Same number of protons, different number of neutrons is an isotope. So you have elements with slightly different masses. And let's talk about mole. Talk about much more later. But a mole, this is sometimes referred to as the chemist dozen. So the chemist dozen, we atoms are really tiny, so we come up with this huge number. Well, Avogadro did. It's 6 times 10 to the 23rd. So that's a 6 with 23 zeros after it. You should think of two things. First thing, like that's a huge number. That's the first thing. Second thing is, wow, atoms must be very tiny. So since they're so tiny, we come up with this huge number to deal with them, and that's a mole. And uh, then molar mass. So the amount of one substance known as molar mass. So for water, and look at the periodic table, hydrogen is 1 gram per mole, and oxygen is 16 grams per mole. So 2 times 1 for the hydrogen plus 16 for the oxygen is 18 grams per mole. So we'll talk about this more later. And we can switch back and forth between this moles and number of molecules. But we use moles very frequently to describe things, which rather than using the individual atoms. So in chemistry class, we use moles much more frequently. Okay, and periodic table. So the chaos here. Dmitry Mendeleev. He is Russian. Look at his beard right there. He's a Russian fellow, and he is the one that started taking elements and linking them up with properties. And even better, he predicted. He said we're missing some gaps here, and I think that these elements are going to have these properties, and he was correct. And here is his periodic table, and it's not very colorful. We have a much better periodic table coming up. Not this lecture, but it's coming up. And an element, here is the periodic table, and this is the element for iron. Fe means iron. Atomic number 26. So that means it's the number of protons, and then the bottom is the terrestrial average for that element, so terrestrial means here on Earth. So the relative isotopes for iron, they're here on Earth, found naturally. You can see here that he predicted. Mendeleev predicted that germanium would look this way. So, and he was pretty much spot on. I'm impressed. Okay, so moving on though, atoms are real, and here's a picture of some atoms. So wavelength of light, you can fit several hundred to 1,000 atoms, depending on the atom, depending on the wavelength of light in them. So you cannot view atoms with light. There's two ways you can view them. You can use an atomic force microscope or a scanning tunneling microscope, also known as AFM for atomic force microscope, STM for scanning tunneling microscope. Looking at this picture, honestly, I can't tell which one is which, because AFMs usually kind of look like candy corn. They're very kind of pointy, and STMs look kind of like pimples. And these look like pointy pimples, so I can't really tell if this is an AFM or an SEM. I'm sorry, STM, scanning tunneling. I think it looks more like an AFM though. So, but you can get atomic resolution with those two machines. And so we can see them, at least we can image them. So atoms are real, so we can see them. And this really brief lecture chapter here, green chemistry. Uh, Point of this course, well, one of the points of this course is sustainability, and we're always looking to improve sustainability. Green chemistry, we're trying to replace rare hazardous substances with more abundant or less hazardous substances. So rather than use up something that we have a finite source of, then with something that's much more readily available, and or something that's less hazardous. So an example of that being here is getting rid of mercury using uh, LEDs instead of mercury compact fluorescent lights. I always wondered about this when there was a big push. I guess I don't know if I'm showing my age here, but we went from incandescent light bulbs using tungsten to using compact fluorescent lights, and I'm like, this is a bad idea because it has mercury in them. So I'm like, we're gonna throw this in the trash dump, and then they're gonna break, and then we're gonna have lots of mercury in the trash dump. So I'm really glad that LEDs have taken off. They use much less energy, and you don't have to worry about mercury with them, which is nice. So this is an example of green chemistry, and it's replaced mercury with something else, and it's even better. It uses less energy, so that's very good for the environment. So it uses less energy in the front, and also disposal is less hazardous. So this is an example of green chemistry and sustainability, where we look to improve the future. And here's the end of that chapter. So see you for the next chapter.